Um, I'm about halfway grading the test, so I think I'm missing 14 out of 32, so a little bit more than halfway. It should be ready by Thursday. Um, Everything else is graded, and I'll tell you the plan for the rest of the semester. So, um, we'll cover sections. So, section A in the graph theory book, section H in the graph theory book, and hopefully my plan is to finish with everything you need for that section today and then go over exercises, examples, practice, and the homework help on Thursday. So I added, let me see, yeah. So I added a list of problems. That's age 24, 25, 7, 8, 9, 36, and 37. So what I'll do, this will become quiz 7. That's our last quiz. And this one really is just, you do all your homework, you have it ready. You'll be asked for one of these problems at random, and I'll grade it. So I will give you 15 minutes because I'm assuming you already have all of it, right? So it's like a 15-minute upload. So when you open the quiz, it will tell you, I don't know, age 27. So you take a picture of age 27, upload, that's it. Okay, so it's more of a homework, but I'm asking you to upload one problem. And so this one is due this weekend. So my idea is that you go over those problems and ask me any questions you want. We'll go over any questions about those problems. Of course, I won't completely solve them, but I will. I will direct you towards the solutions as much as possible. But the idea is that you try them beforehand. Okay, so that's it for section H. We'll finish this week everything, and then we'll cover in the last 2 weeks. We have 4 more sessions after that. We'll cover section H of the combinatorics book. And so this one is Polya's counting method. We're going to count colorings of symmetric figures. There is a lot of algebra there. Um, Algebra that you should know. It's not very complicated algebra, but if you've taken abstract algebra, then I'm hoping that you will be able to make some connections. Not that you require it, right? If you have taken it, maybe it will be a nice example to make connections with that class. So this is Polya's method. Is in the combinatorics book. And for this one, instead of a quiz, we're gonna have wikis, but we'll do it in groups because these problems tend to be much longer. They have, the method requires you to go through different stages. So we'll do wikis in groups of 3. So because I know it's important that you work with, if possible, with people that you feel comfortable with. I have a question of the day today, due today, anytime today. This is the last question of the third and last one. Question of the day. Again, you get 2 easy points. And I'm just asking you name 2 people if possible, you can say no preference or whatever, and so that just will allow me to set up the groups. Okay, so name two people you'd like to work with. Okay, so that's essentially it. Again, I even say in the question, if no preference, say no preference or something like that. So you get the points. So even if you don't have a preference, let me know. So you get the points and then I'll know. All right. So I'll set up the groups and I'll assign you a problem from that section. Anyways, the selection of problems. So because as usual, all problems are essentially assigned to everyone, but you get correct solutions of everything through the wikis. These ones are 50, 51, 57. Those are on the strings. 60, 67. Those are on a grid, on a 3 by 3 checkerboard, I guess. You'll see what this, we haven't talked about any of this, so maybe this doesn't make much sense to you right now. I'm sure it doesn't make sense to you right now, but when we get to it, it will. So these are for the cube, and 79 and 80 are for some spheres. So when we get to it, I'll explain. Right now, I can't really, but there are two stages to these problems. So these are due in two different times. One is going to be on the following weekend. So this weekend, that's a Saturday 5-1. This is a Saturday 5-8 and 5-15. Again, so every problem, like the first stage of every problem is due on 5-8, and then not 5-15, 5-12. What the hardest, I think, the first stage is almost like the setup of the problem, but that's the one that takes, um, I don't know, I think takes the most conversation among the members of the team, and it takes a little bit longer. But once you have that set, and my idea is to correct the wikis for that part as soon as possible, so that you can have the second part by 5-12. The second part is essentially the algebraic part, very algorithmic. So it should be very quick after the first part is correct. But I need to make sure that the first part is correct before you go into that one. So this is a Saturday. So I'm trying to have everything ready. Hopefully it will work out by the end of the weekend. And then you'll have a couple of days to work on that second part, which is, again, very algorithmic. The thinking part, the tricky part is on that first stage, not on the second one. Okay, but I'll explain more when we get to that section. Right now I can't really, but so just as a plan. And then we'll have a review and we'll go over all of this on 5:13. So 5:13 is our last meeting class. We'll have a review for the last midterm, and we can also go over any questions on those wiki problems. Anything that's missing, any questions you have, I want to use that last day, and then we have the finals week. It's not a final, third midterm is on 5:18 during finals week, and I'll have instructions for that. Once we get closer to it. Okay, but this is like just the plan, so you know what's coming. 2 more assignments and the midterm. Okay, so let me continue with planarity and tell you what we're missing. Last time, let me go back to what we had last time. We defined planar graph as a graph that can be drawn without any crossings. Remember that a crossing is just something like this, right? So that's a crossing. So a planar graph is something that you can draw without that. So for instance, this graph that we had last time has crossings, but it is planar because we can draw an isomorphic copy of it with no crossings. This is a plane diagram. This is a planar graph because it admits a plane diagram. So the smallest example of something that's not planar has 6 vertices. So anything with less than 6 vertices is planar. Any graph with less than 6 vertices is planar. This is the first one that isn't. So I want to show you how one way, we're going to learn essentially 3 different ways in which you can prove that something is planar, proving that's, or not planar, actually non-planar. Proving that something is planar only requires you to draw the plane drawing. That might be hard, but that's all you need. You just show it, that's it. Proving that something is non-planar is much, much harder in general. It requires some logical argument. And so we'll learn 3 techniques that don't necessarily apply to any graph. This is a very hard problem for, arbitrary graphs. But it will, one of those 3 will apply to the exercises that you have in the homework, for example. The first technique is related to starting with a Hamiltonian cycle. So a Hamiltonian cycle, we went over that last time, is just a cycle that goes over every single vertex exactly once. And then because, if you assume that your graph is, your drawing is plane, then your Hamiltonian circuit has to look just like that, like a convex polygon, like this blue one. And the remaining edges are completely contained inside or completely contained outside. Because if one of those edges is, part of it is outside and part of it is inside, then it will need to cross the boundary, and that boundary is made of that Hamiltonian cycle. So that's the idea of this first proof. So let me move to a new slide for this H5, proving that K33 is not planar. Okay? So how do we do this? First, so let me say this is technique 1, using a Hamiltonian cycle. Okay, so first I need to find a Hamiltonian cycle. So I'm going to highlight one here. It's not necessarily unique. I just need one. So 1, 2, 3, 4, 5, 6. So I'm going to label my vertices so that I can refer to them. I'm actually going to go in the order, in alphabetical order, as I traverse my cycle. A, B, C, D, E, F. Not that it matters, but it allows me to do things in a more organized way. So I'll say assume by contradiction. Oh, we'll prove the graph is not planar. K33 is not planar. So we say assume by contradiction that there is a plane drawing or diagram of K33. So this is going to be my plane drawing. In that drawing, the Hamiltonian cycle A, B, C, D, E, F, A cannot self-cross, right? Because there are no crossings. So It cannot cross itself. It cannot cross anything. In particular, it cannot cross itself. So now I have here, it's 6 vertices, so I'm just going to draw it as almost regular hexagon. A, B, C, D, E, F. And then there are 3 more edges missing. Those I'm going to highlight in red here. I'm missing this one. I'm missing this one. And I'm missing this one. So those are the 3 edges that are missing. AB, AB, BE, and CF. So those are the red ones right there. That's my Hamiltonian cycle. So because the drawing is plain, again, there isn't one. We're assuming by contradiction that this one is. Because this plane because this drawing, sorry. Because this drawing, because this is a plain, it was okay. Because this is a plain drawing, then each of these edges is completely contained in the interior or in the exterior. Or of the Hamiltonian cycle. And then we talk about this, that without loss of generality, you can assume that one of those edges is in the interior, and then you can play with the others, or in the exterior. Mm-hmm. So without loss of generality, assume AB is in the interior. So now I have AD. AD is in the interior. To avoid crossings, again, this doesn't have any crossings, then BE must be in the exterior, right? Because if I try to join these two, BE, right? So if I try to join this ones, it doesn't matter how I do it, there's going to be a crossing. So BE has to be in the exterior, and it really doesn't matter if it goes that way or if it goes this way. Mm-hmm. You'll see that we still get a contradiction. But for now, just for illustration purposes, I'm gonna do it like that. And then, but then let's see what happens when you try to add CF. CF creates a crossing with a P if it is in the interior, or with BE if it is in the exterior. Which is a contradiction. There are no crossings, right? That's my proof. So I can just conclude therefore K33 is planar. And yeah, going back to my picture, If I try to join Z to F in the interior, I have a crossing right there because they're on different sides of that line AB. If I try to join them in the exterior, then I'm going to have a crossing with BE. And it doesn't matter if BE, it doesn't matter if BE is actually like going around like this. I will still create a crossing with FC in the exterior.
Just to be clear,
Go ahead.
Let's see.
we're proving it is or is not planar.
Oh, thank you. Yes, definitely not planar.
Okay. Sorry.
No, thank you. Not planar. Gulmas?
I was just wondering you say 3 edges is contained in the interior or the exterior. And so what I interpreted that as is like all 3 have to be on the outside or all 3 have to be on the inside. But
I see. So each of these edges.
So you mean like it alternates? Or?
No. So what I mean is that you cannot have a single edge being in both places. For example, AB, it starts here, goes in the interior, then goes out, and then here. You see these edges in both the interior and exterior, so this doesn't happen.
Okay, that's a funny edge, but yeah, I get it.
Yeah, so a single edge cannot be intersect, cannot belong or cannot be partially in the interior and exterior. Like this. Of that Hamiltonian cycle. Okay, because then it creates crossings with the border, and there are no crossings. We're assuming that there are no crossings. Okay. Okay. So, this is the first technique that we're going to see. Try this one. K5, K33, and K5 are the smallest graphs that are non-planar, and they're very special because, as we're going to see later, they're essentially contained in a very special way. We'll discuss that later in any non-planar graph. So K3 and K5 are the smallest graphs that are not planar. Oh, maybe I said something wrong before. I said anything with less than 6 vertices is planar. That's not true. K5 is not planar. K33 is not planar. Anything smaller than those is planar. And, 7 vertices and more could be anything. 6 vertices or less, these are the only 2 that are non-planar. Okay? They're very special. We'll see that small modifications of these, small, whatever that means, we'll explain, are contained in any non-planar graph. So that's what will be our third technique. To prove that a graph is not planar. Mm-hmm. So we'll go over our second technique, and then hopefully we can get to the third technique as well today. All right? Okay. Any questions so far? Okay, so for our second technique, we're going to use Euler's formula. You probably heard about Euler's formula before. Maybe you've heard about Euler's formula for polyhedron, for polyhedra, for the key, or especially if you ever went to a talk or you had a class on regular polyhedra. The cube, the regular tetrahedron, the dodecahedron. Maybe somebody mentioned Euler's formula, but we're gonna use Euler's formula for graphs, for planar graphs. So this is it. First, I need to talk about regions of a planar graph. So of a plane drawing. So if I have plane drawing, any plane drawing. So here I have 3 examples. I can talk about their number of vertices. Mm-hmm. So here, number of vertices, number of edges, and number of regions. Okay, so for each of these vertices, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So for all of these graphs, the number of vertices is 6. The number of edges is like, 1 quadrilateral, 1 and 3 extra edges, 1 quadrilateral, 3 extra edges, 1 quadrilateral, 3 extra edges. So 7 edges, all of them. And the regions are just what you see here. So, like that's a region. This is a different region. And then the exterior is another region. So that one has 3 regions. This is a region. Mm-hmm. And this is another region. And then the exterior is another region. This is a region. This is a region. And the exterior is another region. So each of these has 3 regions. The exterior counts as 1 region. So in a plane drawing, because there are no crossings, I have, my edges separate the plane into regions. And what Euler's formula says is that number of vertices. So if I call this B, I call this E. So if I call this B, number of vertices, E, number of edges, and I, number of regions, then vertices minus edges plus regions is always 2. So always 2 when you have plane drawings in the plane.
A couple questions. One, I just want to make sure the exterior counts as 1 region, but what do you mean by exterior?
This. So, this and all the way to infinity. So the rest of the plane. So I have, imagine that, so this is a partition of the entire plane. You have the green, you have the yellow, and everything else is gray. That's the exterior region. The outer region is usually called.
Professor, I have a question.
Yeah.
What if you have a graph like the problem we did before, where it doesn't even look like a shape? It's just where lines are intersecting, like the problem before.
Like this. Oh, for those we cannot define regions. Okay. We only define them for plane drawings. Okay. So for this one, so we cannot define regions here. Once we draw it as a plane drawing, then we can define regions here.
Okay.
So this regions are defined only for plane drawings. Yeah, go ahead. Who was it, Sean?
Oh, I just want to make sure, is regions basically any shape or line or something, like the line, triangle, and square?
They don't have to be like regular polygons or anything. Give me 1 second. Let me just write these regions. only for plane drawings. You see, if you take the plane, draw your plane drawing. So imagine you actually have the entire plane, right? Draw your plane drawing and the vertices and the edges. If I were to remove the vertices, give me 1 second. Where am I? Okay. So if I were to remove all my vertices and all my edges, the plane gets disconnected, right? So imagine that I actually remove the vertices and the edges from the plane. So the plane gets disconnected into what we call regions. So let me see here. If you remove the vertices and edges from the plane, actually of a plane drawing, the plane is disconnected into regions. Those are the regions. So you see, if I only had something like this, and I remove that, then I'm gonna have that region and the exterior. To go from any point in the red region to any point in the exterior, I will need to cross the boundary, and so I'm actually moving from one region to another. Or how can I say this? Imagine that you can actually cut like around the edges and around the vertices. Then if you cut like that, and then just see what happens, the piece of paper is gonna become three parts. This is connected into 3 parts for any of this. For this one, it will be disconnected into 2 parts: the square and everything else. Imagine you actually cut around the boundary of the square. It will disconnect. It will be the square and everything else. If you were to cut around, along the edges, and it's going to connect to the regions. Yeah, makes sense. So
sorry, I got lost in your verbal explanation. But I suppose if I just know 2 of the 3 verbal of the variables, I can apply it into
you can get the
theorem.
But Sean, how many regions do you see here?
Edges, you mean?
Regions.
Oh, regions.
How many rooms, let's say, if these were walls?
Oh, if I consider them like rooms,
yeah.
4?
Almost. You see, you have 1, 2, 3, 4, and the street. The outside. 5. The exterior. That's the one that doesn't really count as a room, but that's a region. So 4 rooms on the outside, 5 regions. Make sense? Got it?
Oh, okay.
Okay. So let's go. You'll get a little bit more familiar with it, but that's what it is. Those are the regions, okay? And so Euler's formula always gives you that magic number 2. 2 regions in my example. That magic number 2. This number changes if you were to draw these graphs in a different surface. So if you draw it in a torus or in a double torus, that number changes, but it's also always the same for that same surface. The one we're interested on here is just the plane, which actually is the same as 4 drawings on the sphere. And that's why this formula actually applies to solids, to polyhedra. We'll get to that. Okay, so there's one more thing that is useful for our purpose, which are the regional degrees. Regional degrees are essentially how big the rooms are, how big the regions are. So here for the green one, it's just the number of sides in your region. So the regional degrees are 4 for that region, 3 for this region. And look, I need to walk around the boundary of my region to know what is the regional degree. So here, in this one, let me copy. Oh, I don't know. Yeah. So let me draw it down here. So for that one, you see, for the outer region, imagine that you're actually walking around it, around the boundary. So what you're going to do is, let's say you start walking here. 1, 2, 3, 4, 5, 6, 7. You see what I did is how many walls you had to walk through. And this wall, you have to go on this side first and then on the other side. So this one actually counts as 2. So 1, 2, 3, 4, 5, 6, 7. Did I do that? 1, 2, 3, 4, 5, 6, 7. Yeah. So this one has regional degree 7. Make sense? So for this other one, so this one is in C, that's 3. This one is in C, that's 4. Just walking around that rectangle on the outside, 4. And then for the other one, see, I have this. We have that. And I'm in the green region, so I'm walking inside. So I go 1, 2, 3, 4, 5, 6, 7. You see? So this one is also a 7. This one for the green one, 1, 2, 3, 4, 5. For the outer one, I just walk around that rectangle, 1, 2, 3, 4. For the yellow one, I'll do it here for the yellow one. It's something like this. And I'm supposed to walk inside. So I'll go like 1, 2, 3, 4, 5. So the regional degree of this one is 5. Regional degree of the square is 4, 4, and 4 outside. So my black numbers in all those figures are my regional degrees. Regional degrees are usually labeled by R1, R2, R3. So I have regions 1, 2, 3. My regional degrees are R1, R2, R3. And we have a theorem that's very similar to the sum of the degrees equals twice the number of edges. Here, the sum of the regional degrees is twice the number of edges as well. And you can see that, for example, for this one right here, when we count the 4, we're counting the edges from the point of view of the green face, in the interior of that green face. And the same for the yellow ones in the interior of that face. But every edge is counted by one of the faces on one side and by the other face on the other side. So every single edge is counted twice. So the sum of the degrees, the sum of the regional degrees equals twice the number of edges. And so this looks very similar to the degree theorem, right? So regional degree theorem versus degree theorem. This one is the sum of the regional degrees. forever. I don't know how many we have, right? So I'll just say this. I'll just leave it like, oops. I'll just leave it open. So the sum of the regional degrees equals twice the number of edges. And for the sum of the degrees is also twice the number of edges. So they essentially, their explanation is essentially the same. But we're going to use this for different things. Anyway, so all of this was building up towards our second technique. Let's see. So, yeah, I left the proving that K5 is non-planar using the Hamiltonian cycle. Now we're going to use the second technique for that one, and you can try so you try the first technique on K5, and we're going to see the second technique on K5. You can try it on your own on K33. So this is our second technique. So using Euler's formula to prove that the graph is not planar, right? So again, we assume by contradiction that there is a plane drawing. And we apply what we know about that plane drawing. Let's say there is a plane drawing. Assume by contradiction that there is a plane drawing of K5. Right? In that plane drawing, Euler's formula applies, right? Okay, so let's see what we know. What's the number of vertices in K5?
5 vertices all with 4 degrees, right?
5 vertices, all of them of degree 4. How many edges?
20.
It's I'll draw a K5 right here. 1, 2, 3, 4, 5. And then we also, this is not a plain drawing, but 1, 2, 3, 4, 5. We have 10 edges.
10, sorry.
So, thank you, Noah. No problem. 10. It's actually 5 choose 2 because it's any 2 vertices create an edge. So, 5 choose 2. So, again, I'll remove this one because it's not a plain drawing. There is no plain drawing. But we're assuming there is. So what do we have? So this implies that the number of regions is 2 minus vertices plus edges, right? So this is 2 minus 5 plus 10. That's 7. Yep. Okay, I need one more thing that I had in my previous slide, but I didn't emphasize. So I'll go back to that one, okay? Well, it wasn't here. Oh, it's because I didn't show you this one because I thought I didn't really need it. So that's Euler's formula I stated before, but this is an important note. which we're going to use right now, if you have a graph that's connected, K5 is connected with at least 3 vertices, then any plane drawing, any plane diagram satisfies that every region has degree greater than or equal to 3. Okay, so this is b greater than or equal to 3, has to be connected. The Euler's formula is actually for a connected planar graph. Mm-hmm. And so every region has degree greater than or equal to 3. So this means that all the i's are greater than or equal to 3. I'll come back to this one, okay? So, but we're going to use it in our proof. So all the regional degrees are greater than or equal to 3 because K5 is connected. So we can apply Euler's formula. It has more than 3 vertices, so we can apply this. So here we have that the regional degrees so I'm going to call that R1, R2, R3, R4, and R5 because we have R5, R6, and R7 because there are 7 regions, right? Satisfy 2 things. 1, all of them are greater than or equal to 3 by my previous note, right? And 2, their sum is twice the number of edges, which is 2 times 10. This is the regional degrees theorem. So what do we have? We have that 20 equals R1 plus R2 plus R7, which is greater than or equal to 3 plus 3 plus 3. All of them are at least 3. And this is 21. That's the contradiction. 20 greater than or equal to 21. Okay? Mm-hmm. So that's the proof. Any questions?
So do you always just use those minimum numbers, or do you have to
from the note? From the note, you mean?
Yeah.
So 3? Yeah. So let me go back to that note. So K5 is not planar. And that's it. Yeah.
So if you can't make those minimums add up, there's no combination that's going to work?
Yeah, so I don't know if I understand your question correctly, but the only way that these ones can add up to 20 is if some of these numbers are less than 3.
Yeah, I gotcha. They
Right?
can't be. Yeah, they can't be greater. I see it. Yeah, thank you.
Yeah, and so just very quickly about this note, if I had 1 or 2 vertices, then this is not true because if I have 1 vertex, then I have 1 region, and that region has regional degree 1. 1 region, and the regional degree is 1. So it's not 3. So for these two cases, it doesn't apply. When I have 2 vertices, and because my graph is connected, it has to be that graph. Mm-hmm. Then here I have also 1 region. And the regional degree, remember, is I need to start walking around the boundary until I go back to my original. So the regional degree is 2. So this node, that's why it's important in this node to say that there are at least 3 vertices. If we have 1 or 2, something weird can happen, but it's just 2 different graphs, right? So we can deal with them separately. As long as you have at least 3 vertices, you're going to start having regional degrees that are 3 or more, all of them. And that's why we can deal with this larger graphs. Okay. Any questions so far?
Sorry, I'm not getting this part. If regions is 7, edges is 10, and vertices is 5, wouldn't that still equal 2? Or...
Yeah. So the contradiction is not here. We use Euler's formula to know that there are 7 regions, exactly 7 regions, because in Euler's formula, if you know 2 of the variables, then you know the other one, right? And in K5, we know vertices and edges, so we can find out the number of regions. Euler's formula, if there were a plane drawing, then that plane drawing must have 7 regions. And that's what we're using here. You know, the regional degrees, there are 7 regional degrees, exactly 7 regional degrees. I label them R1 to R7. But the main point is that there are exactly 7, and each of them is greater than or equal to 3. So the sum is going to be larger than what it needs to be. That's the contradiction.
Oh, it has to be 3 or more, and since the bare minimum for 3 for all regions, or degree 3 for all regions is equal to 21, which is 1 more than needed.
Exactly. But what's very important is that there are 7 3s here. So 7 regions, which came from Euler's formula.
Yeah, so but a region could be a degree 3 or higher, right?
Right.
So that's the tricky part we have to think about. When if the number of edges times 2 equals maybe was 24 or 23, we would have to consider certain regions to be more than degree 3 to make it work, right?
Yeah, if this number were bigger, then we have choices, and some of the curves that we won't see here, but some of the curves for larger graphs to prove that the larger graph is non-planar when none of these 3 techniques work are also based on this type of idea. And they just figure out, okay, what are all the possibilities? How will a drawing with those possibilities looks like? And but we don't have time enough, or it's not the purpose of this class to show you more about planarity, but only the basics. So we're only going over these 3 techniques. Okay, so let's go into our third technique, and that will be it for planarity. So let's see. Oh, one more thing before we go into the third technique. These are the Platonic solids, and that's what I was telling you about before. Euler's formula also applies to the Platonic solids, and not only to those, to any polyhedron, connected polyhedra in the space. Instead of regions, you have faces. So, for example, here, the number of vertices here. You can compute number of vertices, number of edges, and number of faces instead of regions. So faces instead of regions. When you are working with polyhedra. So here number of vertices for the cube is 8, number of edges is 12, and number of faces is the bottom, the top, and the floor around, so 6. And you can see that vertices minus edges plus faces is 8 minus 12 plus 6. So that's 2. And you can check it for all the others. So I'll leave this for later because I really want to go over the third technique. But you see all of these is essentially, all of these problems are essentially, we give you 2 of the parameters, you find the other, or you find something about the regional degrees. I'll get back to this. Okay? Right, so I really want to go over that third technique. which is Kuratowski's problem. So look, this is the theorem, and I need to explain what it says. So, okay, I'll go back to that. If a graph G contains a subgraph, which is either K5 or K33, or a subdivision of one of these, then G must be non-planar. So that's one direction of Kuratowski's theorem, but what I want to focus on is what is this? A subdivision of K5 or K33. Okay? And then I can tell you exactly what the theorem is. So a subdivision is just start with your a subdivision of K5 or K33. You start with your graph, and then so it doesn't matter how it's drawn. You start with your graph. Let's say this is K5. And then a subdivision is just making the edge. You're allowed to change an edge by a path of any length you want. Meaning, now this is K5. This, any of my edges, I can make into a path. I can add vertices of degree 2. So this one, for example, this is K5. This is a subdivision of K5. So you are allowed to break we can add vertices of degree 2 along the edges. So it's not like adding, right? We're dividing. Maybe I can say we can divide any edge by vertices of degree 2. So the edge becomes a path. So you see, while this one has the number of vertices is 5, in this one, the number of vertices is 5 plus the ones that I added, so 11. I'll say 5 plus 6 that I added. It really looks like K5, but it's not K5. Make sense? Now, what's not allowed is to use one of those crossings as my new vertices. So let's see. If I take this one and I say, I add this one, this one, this one, as I did earlier, and I add one of those others, I decide that that's my, one of my vertices that I'm adding. This one has degree, it's new, and it has degree 4. It was a crossing, right? So this is not a subdivision. Okay, fine. So I'm allowed to add extra vertices of degree 2 along the edges, but I'm not allowed to use those crossings as my new vertices. Make sense?
And that's because the degree is not 2, right?
Let's see. Was this Gomez?
Amber?
Well, Amber, go ahead.
Yeah, I was just saying, it's because when you do that, when you add a vertex to the crossing, that vertex does not have degree 2.
Exactly. So do not use the crossings as vertices, as new vertices. And then, was it Elizabeth?
Yeah, I didn't quite get that for the subdivision, how there's the vertices being added. Still kind of confused.
Let's see. You can add any vertices on top of the edges as long as you don't use the crossings as new vertices. So I can take my K5 here. I can take that K5. Can you annotate in your screen?
I don't think so.
Okay, then just pick any edge. Let's say this one right here, and you can just add any vertex on top. That's a subdivision of K5. Another vertex on top of that one. That's a subdivision of K5. This one, whatever you want. All of those are subdivision. At every stage, I have a subdivision of K5. The only thing that I'm not allowed to add as a vertex is this, or that, not the cousins. Make sense?
Oh, okay.
Yeah?
Thank you.
Okay.
Yeah, a little bit.
So don't add those. Now, the degree sequence, that's another way that you can, just, it's not enough to say that you have a subdivision of K5, but the degree sequence of K55 is 4, 4, 4, 4, 4. All of them have degree 4. The degree sequence of a subdivision of K5 is those 4s remain, and then you have 2s. And it can be different numbers of 2s. In that one, 6 2s. You can just add 1 point or 1 vertex or 2 or all that. The only rule is that you place them on top of the edges, but not on top of several edges or 2 edges at once. Okay? So that's a subdivision. And Kuratowski's theorem says, okay, I'll just say, I also put it here. So Kuratowski's theorem says that a graph is planar if and only if it does not contain K5, K33, or a subdivision of these graphs as subgraphs. And the important thing here is that this is an if and only if. I mean, clearly, we already proved that K5 and K33 are non-planar, right? In different ways, different techniques for each one. But we already proved that they're non-planar. And so if that's part of a bigger graph, then that graph won't be planar because that little piece won't be able to be planar, right? So one direction is super clear. If a graph is planar, it doesn't contain this. But the fact that if it doesn't contain this, then it's planar, then that's a difficult part. So this is an if and only if problem. So this brings me to my last technique. Technique 5 is if you want to show that a graph is non-planar, then you find a subgraph that's K5, K33, or a subdivision of them. Right? So let's see. So in each case here, find a subgraph that is obviously non-planar based on what we know about K5, K33. Is the subgraph isomorphic to either K5 or K33? Let's see. So, you know what? Maybe I'll go into this one instead. Yeah. So I'll go back to that one, if not today, next time. But it's the same kind of problem. I just think that these graphs are more interesting for an example of our technique. Okay, so this is the third technique. We prove that those three graphs are not linear. This one's right here. Okay, so for each one, we find a subgraph isomorphic to, so K5, K33, or a subdivision of them. Now, that's not necessarily easy, but once you find it, that's it. You just show it. In that sense, it's easier than the other techniques because you don't have to explain yourself. You just have to show it. So here, okay. So here, this one over here, maybe we'll do this one first. See, the degrees with this graph are 3, 2, 3, 3, 3, 3, and 3. There are no 4s. So if you have to show that there is a subdivision of K5 with K33, you better try K33 because subdivisions of K4 have vertices of the P4. Subdivisions of K5 have vertices of the P4. So for this one, we're going to look for a K33. So we're going to use 6 of these vertices. And the issue is how to find them, right? It's a lot of trial and error, I guess. So here, I'm going to give you a subdivision. I'm going to use that one. For K33, I need 3 vertices on one part joined to 3 other vertices on the other part, right? So I'm going to label 3 of the vertices A, B, C, and the others 1, 2, 3. Okay? So maybe I'll start with this one. So this one, I'm going to use these 3 edges. Here, I'm going to use this 1, 2. And because I'm looking for a subdivision of K33, this is going to be my other edge. Does that make sense? So it's like the edge with one vertex that we use in the middle to make it, to find that subdivision. So look, these are going to be my other 3 vertices. This one, and that one. So let's say this one is A. This one's going to be B and C. Those are one part of my bipartite graph, K33, 3 of the vertices. And then maybe I'll label this one 1, 2, and 3. And then you can see that I have every red vertex is joined to every green vertex by an edge or a path, a subdivision of an edge. So here, B is joined to 1, B is joined to 2, and wait. Oh, yeah. This one, right? B is joined to 3. Those are actual edges. And then C is joined to 2, C is joined to 1, and C is joined to 3. The only one that is not an actual edge is this one. But there is your K33. Okay, so if you want to, you can do, I have my 3 red vertices, I have my 3 green vertices, and then the one edge that's different, see, I have A, B, C, 1, 2, 3, and the one edge that's different is this one. This one has a vertex inside, and then all the others are just like this. That's a subdivision that we found. Make sense? This vertex here is that vertex there. So it's not really a K33, it's a subdivision of K33. So let me give you the ones for the others. Let's try this one.
Professor, quick question.
Yeah.
So it's considered a subdivision because we inserted that one extra vertex that has degree 2?
Yes.
And so when it comes to Kuratowski's theorem, is that to say that it doesn't specify how many vertices we can add? So is that to say we can add as many as we need?
Exactly. We can add as many as we need, but just be careful. As you can see, I didn't add the vertices myself. I used the ones that we had here because I need to find a subgraph, right? So I need to find a subgraph that happens to be a subdivision of K33, but that subgraph needs to use edges and vertices that are already there. As part of my K33, I'm using the red vertices, the green vertices, and that X vertex to make the subdivision, but that X was already there.
Yeah, that one was. Yeah, you didn't actually add anything, but we can pretend we had K33 and you added that one.
Exactly.
Okay,
Thank you.
that makes sense.
Yeah. So let me give you one subdivision of K5 for the first graph, and then you try the other one. See if you find them. Mm-hmm. So for the other one, I'm actually going to try K5. So this is going to be one of my vertices. It has to be joined to the other 4. In fact, those are going to be my 5 vertices. Mm-hmm. The other 2, maybe I won't use. Maybe I will use as part of the subdivision. Okay, so here, each vertex needs to be connected to the other 5. So this one, the center vertex is connected to the other 4, no problem, with regular edges. Mm-hmm. Then, if I look, let's say, at this top left vertex, it's already joined to the center. I'm going to join it to that one. Is joined to this one. And I need to join it to that one, right? I'm the only one that I'm missing. But there is no direct edge. So I'm going to have to use a path. And that's where my subdivision comes from. So I'm going to mark it with a different color just to show you that that's, I'm using it as a subdivision of an edge, right? To connect those 2 vertices. So I started with this one, and then that one is joined to everything now. But this is a subdivision. Right? And then I can look at the third vertex just to do this in order. So this third vertex is already connected to 1 and 2. I need to make sure that it is connected to the other 2 vertices. So I have this direct edge to connect to this one. And I need to connect to this other one. Again, I don't have a direct edge. So I can use, I can use this one. Okay. The one thing that I cannot do is to, use this vertex for the subdivision that connects 3 to, let's say, 4. Okay. Not 4. 4. 4. Huh? So each vertex that's not part of my K5, but is part of the ones that are used for the subdivision, can only be used for one subdivided edge. Okay? And then 4 is already connected to 1, 2, and 3, so it just needs to connect to 5, and I have a direct edge. So there is my subdivision. Okay? So,
Professor?
One. Yeah, go ahead.
Isn't the subdivision you chose have a degree of 3? I'm not sure if you have chosen those as your subdivision, or because from my understanding, that doesn't the subdivision should have a degree of 2?
Oh yeah, I understand what you're saying. So in my original graph, this vertex has degree 3. You are right. But in my subgraph, I'm only, a subgraph is just a subset of the vertices and the edges, right? And so my subgraph is only the part that's highlighted. So my subgraph doesn't have this edge and doesn't have that edge. If you only look at what's highlighted, it doesn't have this edge. So this one actually has degree 2 in the highlighted subgraph. Make sense? Let me see if I can separate this. Okay. Okay, let me draw it here very quickly just to finish. My subgraph is actually these 5 vertices, these edges. So 1, 2, 3, 4. This one, this one, and this one, this one, this one, and that one. That's the subgraph. You see what I mean? So only what I highlighted is here. This extra edge and this extra edge are not part of my subgraph. This subgraph by itself is a subdivision of K5. So we want a subset of the vertices and edges that, if I separate completely from my original graph, is a subdivision of K5 or K3. Okay? Questions? Okay, so let's do this. You have the homework problems. There are only 7 problems. Take a look and see which ones you can solve and which ones you will need help with. I will expect that you will need the most help with the subdivisions. We'll go over that again, more examples and questions specific to the homework on Thursday. All right? But take a look. Not all of them require subdivisions. So hopefully everything else is okay and we can focus on subdivisions. All right? Okay, guys. I'll see you next time. Thank you so much. Don't forget to reply to the question of the day today.
Thank you, Professor.
Thank
Bye,
you.
guys.
Don't forget what?